Now we'll go ahead and finish up our chapter on gases. The next topic we need to discuss is standard conditions. So we learned that we can define some standard conditions such as standard temperature and standard pressure, and these are abbreviated as STP. So we do this in order to compare basically apples to apples. If we want to compare gases, then we can define a set of standard conditions that will allow us to compare ideal gases under the same situation. And our standard pressure is defined as 1 atmosphere, and our standard temperature is 273 Kelvin, or 0 degrees C. Now, if we consider that the standard amount of the gas would be 1 mole, then we can use that information to calculate the volume of a mole of gas at standard temperature and pressure. So remember, ideal gases basically take up the same amount of space, and so we can solve for volume here, where we've got 1 mole, we've got our R, we've got our temperature, which we defined as 273 Kelvin, and we've got our pressure at 1 atmosphere. So we can determine that 1 mole of gas under ideal standard conditions is 22.4 liters, and we can use that as a conversion factor. In other words, 1 mole is equal to 22.4 liters of the gas. And that's at standard temperature and pressure. If the pressure and the temperature varies, then we won't have the 22.4 liters. We also know that 1 mole is 6.022 times 10 to the 23rd molecules, right? And so that means that 22.4 liters would give us that number of molecules, and that number of molecules would give us 22.4 liters. So 1 mole of helium at STP is going to be 22.4 liters. 1 mole of xenon is 22.4 liters. And 1 mole of methane even would be 22.4 liters, whether it's molecular or whether it's atomic. But notice that from the periodic table, we can see that, for example, helium, and we're looking at xenon have different masses. Helium is 4 grams per mole, and xenon is 131 grams per mole, but they're both taking up 22.4 liters of space. So that means that the 22.4 liters of xenon would weigh more than the 22.4 liters of helium. Okay, so assuming ideal behavior, which of these gas samples has the greatest volume at standard temperature and pressure? Okay, and so this actually was the wrong calculation. I may have worked this last time. It was actually hydrogen. All right, let's look at the density of a gas. The density of a gas at standard temperature and pressure can be given by the mass over the volume. The only difference here is instead of milliliters, because gases take up so much space, we use liters. Okay? So if we consider that we have 1 mole of the gas, and at standard temperature and pressure it would be 22.4 liters, then we can define our density as mass over volume, right? And we can see that we can compare the density of different gases, all right, being basically related to their molecular weight, right? Their molar mass or their molecular weight. And so we see here, if we use 22.4 liters as the volume for 1 mole and the different molecular weights, then we can see that the density of the heavier gas would be greater, which makes sense. So the density of nitrogen is 1.25 grams per liter, and helium is 0.179 grams per liter. And that's why a helium balloon will float. Okay? So density is directly proportional to the molar mass of a gas. All right? And the density can be given by the pressure times the molar mass over R times the temperature. We can derive that equation. And we'll do some problems with that in our exercises. Arrange the following gases in order of increasing density: neon, chlorine, fluorine, and oxygen. We see that neon is less dense than oxygen, is less dense than fluorine, is less dense than chlorine, and that's just directly related to the molar mass or the atomic mass of those gases. All right, the molar mass of a gas is given in grams per mole, right? And so if you can calculate, if you know the mass and you know the moles, you can calculate the molar mass. And we can get the we can get the moles of a gas from the ideal gas law. So we'll work some exercises calculating the molar mass of gases by taking the mass and dividing by the moles and getting the moles from the ideal gas law. Many gas samples are not pure, but they're mixtures of gases. Even air, for example, is about 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide. And this would be for dry air. Now, air in the atmosphere isn't generally dry. It's going to have some water vapor mixed in as well. But these are the percentages by volume of these gases and these make up the bulk of the atmospheric air that we breathe. And therefore, mixtures of gases can be considered as, or we can calculate the total pressure of gases, probably a better way to express that, from the partial pressures of the gases. And we'll look at that in just a few minutes. So the total pressure of a gas mixture is going to be given by the partial pressure of each of the gases in that mixture. And that's going to be basically related to the percentage of that mixture. So we're going to see some equations where we can relate total pressure and partial pressures of gases. So let's look at what that means. So Dalton's law states that the total pressure given by a gas mixture is equal to the partial pressure of each of the gases in the mixture. The total pressure of the gas mixture is equal to the partial pressure of, let's say, component A of the mixture, plus the partial pressure of component B, plus the partial pressure of component C in the mixture. Okay? So we can consider a mixture of ideal gases as being a total of each of the gases, which makes sense. And we know that the pressure of a gas mixture is equal to the number of moles times RT over V. And if we consider each of the individual partial pressures separately, we can calculate the moles of an individual gas in a mixture by its partial pressure. So let's recap that real quick. The total pressure of a gas mixture is given by the partial pressure of each of the components of the mixture. And the total pressure, and remember that pressure is equal to RT nRT over V for an ideal gas. And so if the total pressure is equal to the sum of the partial pressures, then we can say that the partial pressure of each of the components is also related to RT over V by the moles of that component. So we can get the moles of a component of a gas mixture from its partial pressure, and we can get the partial pressure of a gas mixture from the number of moles of that gas. All right, and so that gives us some interesting calculations that we can complete using those relationships. The next calculation that we'll do will be with mole fraction. So the ratio of the partial pressures of a single gas contributes to the total pressure, and it's equal to its mole fraction. So if we know the partial pressure of a component and the total pressure of the gas mixture, we can relate that to the number of moles by the number of moles of that component to the total moles. So in other words, the number of moles of a component of a gas mixture is related to the total number of moles of gas by the partial pressure of that component to the total pressure. And we're defining a new property called mole fraction, and that's written with this little chi symbol. So the mole fraction of A of a component of gas is equal to the moles of A over the total moles. Okay? All right, and we'll work some problems doing those calculations. All right, and if we know that the partial pressure of A to the total pressure is equal to the moles of A to the total moles, we can calculate the partial pressure of A from the moles of A to the total moles times the total pressure. So in other words, the partial pressure of component A is equal to the moles of A divided by the moles total times the total pressure of the gas mixture. And we define the mole fraction as the moles of A to the moles total, so we can say that the partial pressure of component A is equal to the mole fraction of A times the total pressure. So we'll use those relationships to do some calculations in our examples. All right, so for example, for air, the partial pressure of nitrogen is going to be equal to the fraction that is nitrogen times the total pressure. If the total pressure of air is 1 atmosphere and the mole fraction is 0.78, in other words, if air is 78% nitrogen, then we can say that the fraction of air that's due to nitrogen is 0.78. Okay, so that would give us a mole fraction of 0.78 times a total pressure of 1 atmosphere. That means the partial pressure in air due to nitrogen is 0.78 atmospheres. Okay, and each of the components similarly. So for oxygen, we have 21% oxygen. That gives us a mole fraction of 0.21 times 1 would give us 0.21 atmospheres. And for argon, we've got 0.01 for the fraction that is argon times 1 gives us a 0.01 atmospheres. And if we add all of those partial pressures up, we get the total atmospheric pressure, which is 1 atmosphere. And we'll work some problems with partial pressures of gases. A gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3 atmospheres. What were the partial pressures of helium and neon? That was 1.5 atmospheres for neon and 1.5 atmospheres for helium, because they have to add to 3 atmospheres and they have an equal mixture. Let's consider deep sea diving. When a diver breathes compressed air, the abnormally high partial pressure of oxygen in the lungs leads to an elevated concentration of oxygen in the body tissues, and too much oxygen can lead to oxygen toxicity. So as a diver goes down in the ocean, the pressure becomes greater, and if he doesn't have that pressure equilibrated by something, the pressure in his lungs will increase the pressure of oxygen, leading to oxygen toxicity. So it's important for a diver to exhale and breathe his heliox mixture when surfacing in order to equalize that pressure as he or she climbs from a deep level to the surface. And we work some problems with that in our exercises. The next topic is collecting gases. Gases are often collected over water because we can displace water and collect the gases, and then we can calculate the volume. But water itself can exist in the gaseous form. That's called water vapor. And so if we collect gas over water, we have to consider the partial pressure of the water vapor as part of that gas mixture. Now we can find out what the partial pressure of that water vapor is by looking at a chart like this, because the partial pressure of the water vapor is due to the temperature at which we collect the gases. So for example, at 30 degrees C, the partial pressure of water would be 31.86 millimeters of mercury. And remember, 1 millimeter of mercury is 1 torr, so that's 31.86 torr. So if you collect a gas over water, you need to consider how much of that is water vapor, and you'll do that from a chart like this by looking up the value. So here's how gases are collected by water displacement. Here we have a reaction of zinc in HCl. Hydrogen gas is evolved and collected. The hydrogen gas is collected in a tank like this, where we have a beaker inverted in a watch glass, or rather a crystallizing dish. In the beginning, there was no gas in here, but as the hydrogen gas evolves, the hydrogen gas displaces the water, and the water vapor begins to also fill up the space, and the amount of water vapor is going to be due to the temperature. So remember, the total pressure of the gas mixture is going to be equal to the partial pressure of each of the components of the mixture. So in other words, the total pressure of this mixture would be equal to the pressure of hydrogen gas plus the pressure due to water. And we can calculate the pressure due to water from that chart we just saw by knowing the temperature. So that's called the partial pressure of the water. Now we worked some problems with that in our exercises. Next we'll discuss gases in chemical reactions. So we can calculate gases, we can calculate different quantities of gases from chemical reactions. Remember, the chemical reactions give us moles. So from the moles we can calculate, say, the volume. And from the volume, we can calculate moles. And we have a couple of different examples that helps us to do this. And we can convert one gas to the other by the balanced equation. So it's important to have your balanced equation in order to do these calculations. All right? So let's look at that. So if we have, let's say, a mass of A, we can convert that to moles of A, and then to moles of B, and mass of B. So we did that kind of thing last semester. But if we instead are starting with the pressure, volume, and temperature of gas A, we can convert that to moles of gas A from our ideal gas law, and then to moles of B from the balanced equation. And then if we want, if B is a gas, we can convert that to the pressure, volume, or temperature even of gas B. If we're at standard temperature and pressure, we can use the identity that 1 mole is 22.4 liters. How many grams of water form when 1.24 liters of hydrogen gas at STP completely reacts with O2? So we can actually do that calculation. Let's go ahead and look at that. All right, so we've got how many grams of water form. We're looking for grams of water, but we're starting with 1.24 liters of hydrogen gas. So 1.24 liters of H2. All right, and so how do we start this problem? We've got to convert the liters to moles. And we're going to use our PV equals nRT equation. Okay, but since we're at standard temperature and pressure, let me rephrase that. We can use the PV equals nRT equation. But since we're at standard temperature and pressure, we don't need to do that. We can use the identity that it's 22.4 liters per mole, right? And so we have liters here. So we're starting with 1.24 liters. And we've got 22.4 liters is 1 mole of H2. Now we can use our balanced equation. 2 moles of H2 to 2 moles of water. 2 moles of H2 gives us 2 moles of water from our balanced equation, right? And we were asked to find grams of water. So water is 18.02 grams if you add it up from the periodic table per mole. And then we can find the grams of water. So I didn't do this one in advance. Let me just go ahead and get my calculator here. And I got 0.998 grams of water. Okay, so let's read this problem. Nitrogen and hydrogen react to form ammonia according to the following equation. N2 plus 3H2 yields 2 ammonia. Consider the following representations of the initial mixture of reactants and the resulting mixture after the reaction has been allowed to react for some time. If the volume is kept constant and nothing is added to the reaction mixture, what happens to the total pressure? So let's see what's happening. We have 1 mole of nitrogen plus 3 moles of hydrogen going to 2 moles of ammonia. In other words, we've got 4 moles of starting material going to 2 moles of product. Okay, so let's think about our PV equals nRT equation, right? So we're going to fewer moles. How is that going to affect the volume? Okay, so let's solve for moles. N is equal to PV over RT. So if the moles goes down, the volume is going to what? Go down, because they are directly proportional. So the pressure, I was answering the wrong question here. So moles is also directly proportional to pressure, and so if the moles goes down, the pressure will also go down. All right, so the pressure decreases.